I'm Juha Kökkä. I'm going to introduce the greenhouse gas emissions estimates from the energy sector. In this presentation, we are going to go first through the role of energy in the global greenhouse gas emissions. And then we will have a look at the international standards covering both the energy data and then the emissions estimates from that energy data. Then we are actually going to look at the methodology itself. Then we'll have a couple of points on data quality, because it really affects the estimates we will have in the end. And then we have mentioned a couple of other useful metrics. And lastly, we will wrap up with some key takeaways and also some Menti questions. And if you have any questions, feel free to raise your hand and ask questions also during the presentation. Thank you. So to start, energy in the global GHG emissions. As we see here, we can compare the source category of energy to the other source categories and the total greenhouse gas emissions globally. And we see that both in the 90s and also now, energy is the major part of the global greenhouse gas emissions, accounting for 3/4 of the total. So energy is very important when tracking emissions and also when considering how to reduce the greenhouse gas emissions. And to define what we mean by the source category of emissions, or what source categories there are in the IPCC guidelines. Basically, the greenhouse gas inventory under the UNFCCC convention and under the IPCC guidelines consists of energy, industrial processes and product use, agricultural, forestry and other land use, and waste. In this presentation, we are going to look at energy, and specifically under energy at 1A, fuel combustion activities. We also have under energy emissions the fugitive emissions from fuel production, for example, flaring, etc. But those we are not considering in this presentation, and neither are we considering the carbon dioxide transport and storage. So to start, you may return to the Menti. I will probably need to restart the presentation after Sonia, so just a sec. But you can see the question will be, which sector was the highest emitter globally in 2022? Transport, power generation and energy industry, industry, or buildings. And just in a second, you should see it also in the Menti side. So I'll give you a second to log in back if you have closed the Menti app, so you can here see the code. It's the same code, so you can continue if you are still logged in, but if you're not, you can log in with the 374811100. Okay. I will continue to the actual question. So, which sector was the highest emitter globally? Feel free to put your answers there. So we see some answers for, a lot of answers for power generation, some transport, some buildings, and not many for industry so far. Okay, some answers still coming in. I'll give 15 seconds more to see that everybody gets an answer. Okay, so it looks like most common answer was the power generation, energy, and energy industry. And then we have some for transport, a little bit industry and buildings. Oh, well, let's see what the data says for the global value. So actually, globally, most people were correct that power generation and energy industry own use has been the main sector out of the energy emissions. So here we see that that the shares by sector have changed a little bit. Power generation has even gotten a bit higher share since the 90s. But if you look at the graph on the right, we can see that, for example, the building sector and the others, which includes here agriculture, forestry, fishing, and other non-specified, those have relatively changed less than industry, transport, and power generation. And we can indeed see that the after power generation, transport, and industry are the next sectors. And the sectoral split of emissions really also is an indicator on the economic structure of a country. Some countries where there's lots of, let's say, production of fossil fuels, transport may be high, because actually that also includes the transport of the fuels, and there's emissions associated to that. For some other countries where industry is a major sector, of course, industry emissions will be also higher. Okay. Next, we are going to look at the international standards, specifically the IPCC guidelines and the IRES. So the international recommendations on energy statistics are the global reference for energy statistics methodologies. These are basically what, if you were listening yesterday already, the building of energy balance, and also what Senja explained about the energy balance, this is where that comes from. And then we have to get from that energy balance to the emissions estimates. We have the 2006 IPCC guidelines for national greenhouse gas inventories. And these are aligned with IRES. So if you are collecting energy data according to the IRES standard, you may use that energy data also to estimate emissions from energy according to the IPCC guidelines. And IEA is contributing to both of these methodologies. So to move forward, what are actually the methodologies to estimate emissions from energy? I see there was a question in the chat, but I think I'll maybe answer it after this section. So if somebody doesn't answer in the chat already before. So to estimate emissions, we need quality energy data. According to the IPCC guidelines, we have two main approaches to estimate fuel combustion emissions. We have the sectoral approach, which is the more detailed one, the most detailed one. It's a bottom-up approach where we get economic activity or the energy data, the demand data, as Sonja explained before, demand being the transformation and final consumption. And this we have for each sector and each product. And then the reference approach is a top-down approach from the energy supply data. And because of this of course, it is a less granular approach. But still, even for the reference approach, we want to have data for each of the products separately. In both of these approaches, it's very important to exclude the non-energy use of fuels. This is an important step because, for example, if a fuel is used in the manufacturing of chemical products, let's say plastics or paint or whatever, these will not be combusted, and the carbon doesn't end up in the atmosphere with the same process that we are following here. So we want to be exact with what we are measuring. And the sectoral approach can include all greenhouse gases from fuel combustion, while the reference approach, by definition, can only include CO2 emissions from fuel combustion. Now we have a look at the reference approach methodology. The key here is the principle of carbon conservation. We know the carbon inputs into the national economy, so the energy supply by product, and then we assume that it's 100% either released in the atmosphere or diverted, so stored in different products or in the fuel stocks. And this is useful to benchmark and check the results from the sectoral approach, but this should not be the primary approach. The primary approach should be the sectoral approach, because this is the one with more detail, which gives more information on the economy, on how things work. So you can see here also the carbon conservation principle, which means in this case that we know the mass of carbon contained in the fuel that's combusted. Then we know how the carbon is preserved and oxidized. So we know also the mass of greenhouse gases produced. And this means that by the energy units combusted, we know the amount of emissions released. And this gives us the emissions factor, which is defined here by the mass of greenhouse gases released per unit of fuel combusted. And this emission factor is fuel specific, of course. So for each type of fuel, each quality of fuel, we will have a different emission factor. And now we continue to the IPCC Tier 1 methodology, where we use, you can use default emission factors in case we don't have access to more detailed emission factors for fuels. And we will have the total fuel combustion emissions when we sum over all of the sectors and fuels, the physical amount of fuel combusted, then multiplied by the net calorific value to get the energy amount of, or the amount of fuel combusted in energy units. So here a net calorific value is important for that. And then we multiply by the emission factor to get the resulting emissions. And for each fuel, we have a different net calorific value, and it's important to collect data also on these, because this allows us to be specific with the fuels when calculating emissions. One side note for countries where biomass is used, under the IPCC guidelines, the CO2 emissions from biomass combustion are not included in the national totals in the energy sector. They are estimated, reported in the agricultural, forestry, and other land use sector. But for methane and nitrous oxide, these emissions should be estimated and included in the energy sector. So there's a split here with the carbon CO2 emissions, and then methane and nitrous oxide. And now we can go to data quality, but let me quickly check the chat if there's something that should be answered. I see Roberta had answered.
Yeah, please, Juha, continue your presentation. Then at the end, we do a wrap up in the Q&A because we are a bit late. Thank you.
Yes, okay, let's do that. Thank you. Let me continue. So how IEA estimates basically emissions from the energy data, and this is also the process if you follow the IRES and then the IPCC. So we have the data collection from National Energy Statistics, from where we get to energy as a statistic, as a commodity, physical units of energy used in the economy. And then these are using the IRES reformatted and using the net calorific values, then multiplied to energy units, which gives us energy balances where the everything is in energy units and arranged into this sort of table format that you are now familiar with. And from here, we are able to use the IPCC guidelines and the emission factors to estimate the greenhouse gas emissions. And because of this, I have to re-emphasize that the net calorific values are very important, because as it is a multiplier in the equation, if you have 10%, 15% inaccuracy in the calorific value, that will also reflect in similar way to the emissions estimate. So we should also, in addition to collecting energy statistics in physical quantities, we should also collect the calorific values. Another important factor is to have a sectional breakdown. So here you can see, for example, the transport under the UNFCCC inventory tables, which follows also the source categories of the IPCC. You may see here the transport split by multiple subsectors, seeing road transportation split into cars, light-duty trucks, etc. So it's in order to understand specifically where the emissions come from and, for example, which kind of emissions factors and fuels are consumed there. It's important to collect all of these disaggregated data. And additionally, as mentioned, it's also important to follow the Standard International Energy Product Classification, or SIEC, which is part of the IRES, in order to also have standardized definitions for different energy products. This is especially important if you are using default emission factors from the IPCC, because you need to make sure that your definition or the data you're collecting for a product and then the product that you're actually using the default emission factor for are the same product. So you need to have a very good understanding where the energy products used in the country are mapped in the SIEC classification. And to mention quickly some other useful metrics, we can look at the macroeconomic drivers of CO2 emissions, or the more well-known Kaya identity, coming from the name of the person who developed this. And here we can see that we basically can derive a connection between the CO2 emissions and then population, the GDP divided by GDP per capita, then the energy intensity of the economy and the carbon intensity of the energy supply. And we can see here the trends that increasing population and GDP per capita have been driving the global emissions upward. Another interesting metric to follow in the country levels is the electricity emissions intensity of the electricity grid, where you can divide it to multiple scopes. There's actually 3 scopes. So I'm quickly going to cover 2 of them here, where the first scope under the GHG protocol, which is a standard that covers the grid emissions intensity, is on-premises fuel combustion. So if you have a factory which is combusting fuels as part of the processes, this will be on premises. But then if you're using electricity from the grid, you need to add to that the emissions from producing that said electricity. And here in the scope 2, we have the average emissions intensity of the electricity grid, which is going to give an emission factor for the electricity generation. that can be used to then estimate the emissions from the electricity consumption. And key takeaways before Menti questions. So, as mentioned, the sectoral national energy data are the primary source of GHG emissions estimates, and this needs good resourcing and good planning between different agencies and branches of the government so that it's certain that the same data are used for energy statistics and emissions estimates with the same methodologies. And as mentioned, IRES and IPCC are aligned. So starting from IRES using that makes it also easier then to later estimate the emissions according to the IPCC guidelines. Some focus areas for countries to improve emissions estimates include timeliness of data collection. For example, sometimes monthly energy data may be available. And then to improve accuracy and international comparability, you first should reduce statistical differences and try to understand where those come from. Then to update calorific values, make sure those are accurate. Use the SEEC classification of energy products and use the IC classification of economic sectors, or to align with the UNFCCC CRT tables split of sectors also. And then, as said, it's important to track the non-energy use of fuels, so we are not accidentally including fuels that are not combusted into the fuel combustion emissions. Okay, thank you.